Transformer calculations. A transformer is one of the most efficient devices used in electrical transmission and distribution. It is used to step up or step down voltage or current. A transformer is efficient because input power is equal to output power. The construction of a basic transformer. Transformer consists of two coils, the primary and the secondary. Each coil has on it circuit components. As we examine it, the primary circuit has primary current known as IP, input voltage known as EP or VP. This of course is a symbol of the source, which is alternating. Number of turns, primary, designated by NP. This is now a laminated steel core that is used to separate between the two coils in a transformer. The secondary circuit, much like the primary circuit, has secondary current designated by IS, number of turns secondary NS. The load is designated in ohms, which stands for impedance, and impedance is the resistance of an transformer circuit. Okay? Then you have output voltage, which is given as ES or VS. Ohm's law, as we would have discussed earlier, is summarized in two formulas. The voltage formula, where we have V or E over I R, as well as the power formula, which has power over current and voltage. In this case, Z would be substituted for R in this circuit, but both of them indicate resistance. Transformer ratios are given by the following ratios. The turns ratio is the relationship between any value that is on the primary and its coefficient on the secondary. So you will have number of turns primary over number of turns secondary is also the same as voltage primary over voltage secondary. It's also the same as current secondary over current primary. These ratios are used to calculate turns ratio. Now let's do an example. In this example, we have a simple transformer with 3,200 turns on the primary and 80 turns on the secondary. It also has an impedance of 100 ohms. It is supplied by an input voltage of 1,448 volts. You are asked to calculate the turns ratio, the voltage secondary, the current secondary, the input power IP, the current secondary, the current primary, The efficiency of the transformer must also be calculated. So the first thing we will do is calculate the turns ratio. To calculate the turns ratio, we remember our turns ratio formulas. So we know turns ratio is equal to number of turns primary over number of turns secondary. It's also equal to voltage primary over voltage secondary. It's also equal to current secondary over current primary. With that in mind, we must now find two values that are both on the primary and on the secondary. And so we have it here, number of turns primary and number of turns secondary. So we will use this first formula or this first ratio to calculate our turns ratio. Therefore, substituting the values, we will have 3,200 divided by 80. We can cancel the 0 out, and we have 8 into 320, and that should give us 40. So our turns ratio now is 40 to 1. What does that mean? It means that for every 40 turns on the primary, you make 1 turn on your secondary. Hence, this transformer is a step-down transformer. The next part of the question requires you to find voltage secondary. To find the voltage secondary, we look at our diagram again and see what we have. We have voltage primary, and we now just calculated turns ratio, and we have a formula here that describes the relationship with voltage primary and voltage secondary. So here goes. Turns ratio, TR, is equal to now EP over ES. That means turns ratio, which we know is 40 over 1, because of course a ratio can be represented as a fraction, is now going to be multiplied by EP, which we know as 1448, and that's going to be divided by ES, which we do not know and are trying to find. We will now cross multiply. We get 40 ES is equal to 1448, and of course we know these are volts. So ES now, by bringing the 40 over, will be equal to 1448 divided by 40. ES is equal to 36.2 volts. That now is our secondary voltage. 1448 volts divided by 40 will give us 36.2 volts. 36.2 volts. That takes care of voltage secondary. The next part of the calculation requires us to find IS. IS, of course, is your secondary current. Now, to find this, we cannot use our turns ratio because we do not have a primary current. What we will have to do is to treat the secondary circuit, and of course the secondary circuit is always the one with load, treat it as a separate circuit. We would have not just found ES and could put ES to be 36.2 volts. Having done that, we can now use Ohm's law's formula for voltage, which will have E at the top, I, and in this case we are substituting R to be Z. So we are now going to say IS, which is now, we cover I is going to be E over Z. E secondary over Z. Remember we said Z and R is the same thing. So ES now is 36.2 volts, and we are dividing that by the ohms we have here, which is 100 ohms. So IS, by doing a simple math, will be equal to 0.362 amperes. Okay, simple. So having found IS, we can now use turns ratio to find IP. So turns ratio is equal to IS over IP. Therefore, 40 over 1 times IS, which we know is 0.362 all over IP, we say 40 IP is equal to 0.362, running out of space, right? Therefore, IP is now equal to 0.362 divided by 40. And this is now going to give us will now give us 0.00905 amperes, small values of current. Okay, amperes. Okay, amperes. Now, okay. Now, the last thing you're asked to find is the efficiency. Now, efficiency is calculated by saying power in divided by power out. That's in percentage. So therefore, to find this, let's use this small space here. We say the power in is going to be the same as IP times times EP. The power out is IS times ES. So we can just plug the values in easily. So IP, which we have calculated here as 0.00905 amperes, times EP, which we know is 1448, divided by ES, which we know, alright, let's do IS, which we know is 0.362, times ES, which is 36.2. Let's see what we get. So we get 13.1044 at the top and at the bottom. To make this a percentage, of course, it would be, we would have to multiply this value by 100 over 1. So times 100 over 1. And these cancel out, so 100. So your transformer is going to be 100% efficient, which follows through with what the transformer principle is all about.